everybody. Welcome to the SESME discussion about the Smart Manufacturing Additive Manufacturing Program. This is a program that was run by Honeywell in order to kind of further the development of the data recording, data analytics applied to data being measured off of laser powder bed fusion. This is an area that's very important kind of as a need for laser powder bed fusion, because what we have now in the current situation today is there's measuring equipment on laser powder bed fusion parts or equipment, and yet folks don't really know exactly what is really needed in order to ensure a part is high quality and have the most efficient manufacturing methods. So additive manufacturing being fairly new, there's not a lot of history. If you look at all these conventional manufacturing processes, there's a lot of history there as far as how do you make a good casting, for example, and what things all of a sudden make a bad casting. You don't have that in additive. So the need is really there for collecting data during the build process and analyzing that data efficiently. And that's really the purpose of this program. And obviously, if you improve yields, now you don't have to build as many parts. You have less parts that are partially built, and then you stop at the part because now you recognize you built a bad part. And so that will save energy there. So really, it's applying the new data analytics methods such as machine learning, but it was also to identify those data streams. We know in all these situations where you are measuring some sort of data off a factory floor, it's very important that you have a good, accurate sensor measurement and you know what you're measuring. If you're measuring something that has very little value or very little impact as to the quality of the process, then all that hard work would be for nothing, right? So that's the whole purpose of it, is really collecting the data, analyzing the data, and quickly getting those insights back to the operator. We had teammates certainly in the program, USC, UCLA, Missouri Science and Technology. We had other programs like Identified 3D CAM, who were really in there to help support the program. But really, we started by looking at the different data streams that people have been looking at. And those data streams include layer pictures. As an example, the equipment builders and most equipment, my experience is very good, but they take pictures of every layer, but they don't tell you what those pictures mean. And there's no efficient means to sort through those pictures to decide which of those 10,000 possible images. There were part 10,000 layers, you have 20,000 images. So we created an ML algorithm that basically went in there and screened those layer pictures, and it might pull 7 or 8 or 10 and show them to the engineer and say, okay, look at these 7 or 8 or 10, because these could be hinting at a possible part defect. So we did that, and that was successful. We also determined, based on analysis of part root cause defects, that encoder jams are really one of the big issues that we have. And so we did add sensing capabilities for encoder jams. It was kind of a slight addition to the program, but we were able to fit it into the original scope, and so that was good. It says we work with us very well, improving that. And so now we were in a position to be able to predict encoder jams, and that's when the wiper blade that spreads the powder interferes with the part and maybe stops working. In theory, that could scrap a part. And so predicting those encoder jams is a big cost savings for folks. We also looked at melt pool analysis, other thermal analysis in order to see if we could detect part distortion. And we were able to do some of that. More work needs to be done in those areas. Been a lot of programs that have looked at melt pool. In my Celsius. Layer pictures are important. Probably overall temperatures are important. The coater jams are important. For research on new alloys, certainly melt pool it could be helpful. But really, it's those first three that we believe are really the best way to go there. So certainly from a standpoint of impact, if you can save a part that's 80% built, and now you can stop or coater jam and do a correction on the fly, that's going to save a lot of energy. Our measurements show that about 25%, 30% of new part builds are failures. And if you could prevent even half of those, then you're going to save 15% of the energy during the development phase. So certainly from a benefit standpoint, we're going to now know better which sensors to go after, which data streams to go after. Now have a means of showing to the engineer on the floor. We did create a user interface that kind of can format the data to get them at their fingertips some means of looking at the data quickly. Certainly, it's helpful to the AM community because in order for AM to be successful, it absolutely needs to have access to these data streams, and it needs to efficiently look at these data streams and use them to make better processes. Because think about it, every AM part is kind of a new part, right? 5 years ago, there was no AM laser powder bed fusion, at least not in production. So now the potentially hundreds of thousands of parts that will be developed over the next 20 years, they're all starting new. And so we need more efficient means of developing parts. And so this will be helpful to people. And the truth is, for people buying equipment, they can say, gosh, they want to charge me $100,000 for that data stream collection system. And I now recognize, based on this study, that that's maybe okay for research, but it's not good for production, not production. So it helps you save money in terms of buying equipment, and it saves energy in terms of needlessly putting some system on a production piece of equipment that you don't need. So I think it's a very practical program, something that we looked at, helping the engineer and the operator make better parts sooner than later. And it really is not a program that was designated in previous programs. If you asked what the differences previous programs looked at, a lot of melt pool analysis and loved physics and loved talking about the physics of the melt pool. But the truth is that doesn't really have a lot of practical input, not yet anyway, on production parts in improving yield and saving energy. But this program has. So from that standpoint, it's been very valuable for us. And we're happy to share this data with SESME and the SESME membership and U.S. industry, because we really just want access to better quality parts. And if somebody can make a great part for us using laser powder bed fusion and use this in-situ monitoring to make higher quality parts at lower price and save energy, then we think that's fantastic. So we thank SESME for funding the program and our partners for working